Hello my dear students, again very welcome to all of you in your physics class, and in this lecture we are talking about the moment of inertia of a spherical shell. Okay. So, moment of inertia of a spherical shell. So, how to find the moment of inertia of a spherical shell? Okay. You know very well the spherical shell is kind of rigid body. So, if you want to find the moment of inertia of rigid body, it is I equal to integration r square dm. What we have to do? We have to do integration. Okay. Integration of r square with respect to m over the volume. Okay. So, moment of inertia of spherical disc about an axis, it is a spherical shell, not disc, about an axis passing to the center. Okay. About any axis passing to the center. So, what we have to do? In this case, we have to consider some spherical rings, okay, spherical rings over the sphere, over the spherical shell. So, let us consider a differential ring, and the radius of this differential ring is a small r. Since the radius of the spherical shell is capital R. So, we can write here the radius of a spherical shell is capital R, okay, and mass capital M. Okay. Now, we are considering a spherical ring, okay, of radius small r, and the length, the thickness of this differential ring is dl. Okay. Now, if we are considering that this differential ring is making angle d theta at the center, sustaining angle d theta at the center. Okay. This differential ring having differential thickness dl, sustain angle d theta. So, this dl can written as r into d theta. Okay. Actually, in this integration we have to do integration with respect to theta. Okay. When we move this ring from lower end to upper end, okay, from this lowest point to the highest point, okay, we have to integrate with respect to theta. Okay. So, with this horizontal, let us consider this differential part, the radius of the radial vector of differential part is making angle theta. Okay. So, the value of theta at the lowest point is equal to minus pi by 2, and at the highest point theta is equal to pi by 2. Okay. This radial vector will move on the surface of a sphere. So, at the lowest point it will be minus pi by 2, at the highest point it will be pi by 2, plus pi by 2. So, in this case we have to perform integration, we have to do integration with respect to theta, then our integration will become very easy. So, this differential thickness of ring we can consider r into d theta. Since mass is distributed over the surface, so we have to find the differential surface. Okay. Mass is distributing in this case over the surface. So, what we have to do? We have to find differential area. Differential area of ring. So, what is the differential area of ring? Again, it is the total length 2 pi r, okay, the length 2 pi r into thickness dl, and this dl can written as r into d theta. Now, the radius of this differential ring also changing from lowest point to highest point, it is also changing. So, we can write this r here, we can draw a triangle, this is r and this is capital R, and this angle is theta because this angle of this radial vector with horizontal is theta. So, this r can written as r cos theta. The radius of differential ring can written as r cos theta. Okay. So, we are putting value of this small r, which is 2 pi into r cos theta, and differential thickness is r into d theta. So, this differential area is equal to 2 pi r square into cos theta into d theta. This is the differential area. Now, we have to find the differential mass. So, the differential mass dm is equal to total mass divided by total area. Can anyone tell me what is the total area of a spherical shell? Yes, it is 4 pi r square. Yes, it is 4 pi r square, okay, into differential area. Now, we are putting value of differential area m divided by 4 pi r square, and value of differential area is this 2 pi r square cos theta into d theta. So, 2 pi r square cos theta into d theta. What we have to do? We have to do integration with respect to theta. So, this r square pi and 2 4 cancel out, and finally, we are getting capital M divided by 2 into cos theta d theta. It is the differential mass of differential circular ring. Okay. Now, what we have to do? We have to put this formula in this, or we can say the differential moment of inertia of differential ring, moment of inertia of differential ring. So, di is equal to radius of mr square. So, radius is square. So, radius of circular ring is square into dm. So, di is equal to this r can written as r cos theta whole square, and what is value of dm? It is m by 2 into cos theta d theta. I think it is very much clear to all of you. Now, we have to do integration. So, we will get total moment of inertia. Okay. Integration of r square m by 2 cos cube theta d theta. It will become cos cube theta, cos square theta, and cos theta will become cos cube theta. Now, we have to do integration of cos cube theta. Okay, it is very easy integration. So, I is equal to mr square by 2 integration of cos cube theta with respect to theta, from theta is equal to minus pi by 2 to pi by 2. Why it is minus pi by 2 to pi by 2? Because at the lowest point theta is equal to minus pi by 2, at the highest point theta is equal to plus pi by 2. That is why we have to do integration from minus pi by 2 to pi by 2. Now, how to do integration of cos cube theta? What we can do? We can use trigonometric substitution. What we can use? We can use trigonometric substitution. How? Let us see. First, write it down completely. Now, how we can use trigonometric substitution to do integration of cos cube theta? This cos cube theta, I is equal to mr square by 2 integration. This cos cube theta can written as cos square theta into cos theta, cos square theta into cos theta into d theta. Now, this cos square theta, what we can write? mr square by 2 as it is 1 minus sin square theta into cos theta d theta, from minus pi by 2 to pi by 2. from minus pi by 2 to pi by 2. Okay. Now, what we have to do? We have to use trigonometric substitution. We can write sin theta as t. So, the differentiation of sin theta is cos theta d theta is equal to dt. So, this cos theta d theta can written as dt and sin theta can written as t. So, I is equal to m r square by 2 integration 1 minus t square into dt. This cos theta into d theta can written as dt. Now, what about the limit? We have to change limit also. So, how to change the limit? If we are using sin theta is equal to t, okay, sin theta is equal to t, then at theta is equal to pi by 2, this sin pi by 2 which is equal to t1. So, this t1 equal to 1, this t1 equal to 1. So, upper limit theta 1 is equal to 1. Now, at theta 2 it is theta 1 minus pi by 2, theta 2 is equal to minus pi by 2. What we have to do? This sine of minus pi by 2 is equal to t2. So, t2 we are getting minus 1. We know very well sine of minus pi by 2 is equal to minus 1. So, the lower limit is equal to minus 1 now. Now, I is equal to mr square by 2. This portion we have to rub. Okay. Now, integration of 1 is t and integration of t square is t cube by 3. Okay. We have to use limit from minus 1 to 1, or since it is kind of even function, 1 minus t square is kind of even function. So, what we can do? We can multiply 2 and can change the limit from 0 to 1, since it is even function. It is property of even function. Okay. I is equal to, this 2 will cancel out, mr square, upper limit 1 minus lower limit 0. So, 1 minus 1 by 3 minus 0. So, finally, we are getting 2 by 3 mr square, 2 by 3 mr square. Okay. So, it is the moment of inertia of a spherical shell about an axis which is passing through the center. In this case, we are using a concept. We are using a concept in which if we having limit from minus a to a. Okay, I am writing here f of x having limit minus a to a. If this f of x is even function, if it is even function, what you can do? You can write 2 into integration from 0 to a. At the place of minus a to a, you can write 0 to a after multiplying 2, f of x dx. Same concept I am using here. Okay. So, it will become very easy now. Thank you very much.